we want to find any physical problem, we apply Newton's equation. Force is equal to mass into acceleration. And based on the little extension of that one is called your Lagrangian equation, Hamiltonian equation. So all the classical properties in our day-to-day life, they are given by Newton's equation. But in quantum mechanics, if you explain quantum mechanics, you have, suppose a electron is moving in an hydrogen atom or in the some energy level or something. In quantum mechanics, you consider a Schrödinger equation. We shall discuss about this Newton's equation or Schrödinger equation. I have a comparison in my next in some after some time. Next one, you see this experiment is a actually interference experiment, Young double slit experiment. Famously, you have studied in your +2. So you see in the upper part, in the figure A, there is a bullets are coming out. If bullets are coming out through the hole 1 and 2, some of the bullets either pass through 1 or some of the bullets either pass through and 2, and immediately the probability of finding at which cross the hole 1 is P1, and the probability of particle which are coming through hole 2 is P2. Then you will see that they will strike the screen where P probability is P1 plus P2.
They are not audible. Hello? They are not audible.
Hmm. So photons. So photons are actually the light are wave. I know that light is a wave, but it are also particles. Light consists of particles called photons. So these photons, they does not behave like your guns, like bullets. You see from the figure that they show the interference pattern. Somewhere there will be constructive interference, there will be destructive interference, and here simply P12 is not P1 plus P2. It is something different. So here the light is behaving as a wave, but it can also behave as a particle. So everything in this universe is dual in character. Then, but I have a question. The nature of symmetry. Everything in this universe, nature behaves as if everything is symmetric. Then why there will be two sets of laws in micro level in the atomic scale, and another one will be in the macro level? That means in our day-to-day life, when I consider as when I am walking through a velocity v, I am behaving as a particle, not as a wave. But when the electron is moving inside the atom around the nucleus, then it behaves as a particle. It behaves, character can be described by a wave. Then why these two different things? We have an answer for that. What is that one? That is called your Bohr's correspondence principle. The Bohr's correspondence principle tells me that if for very large quantum numbers, the quantum mechanics reduces to classical mechanics. If you observe in this figure, in the previous figure, you see here the simple pendulum, the energy change is continuous. But in your right-hand side figure in the hydrogen atom, you see that ground state is minus, for a single hydrogen atom, it is minus 13.6 electron volt. The next excited state, first excited state will be minus 13.6 by 4. Next excited state will be minus 13.6 by 9, and so on. If this n will become large, first n is equal to 1, 2, 3, 4. If you closely observe, when you goes up and up, you see that the difference between the energy level decreases. And when n becomes infinity, very large number, the energy change is very, very small. So that you think that the energy change is continuous, but it is not happening so. Actually, there is some difference in the energy level, but the energy change is so small that you are thinking that it is continuous. Imagine a point something like this one. You take a simple glass where A suppose it is half full, the glass is half filled, and now you bend the glass and drop 2-3 drops. So it will not affect, you will see that only 2-3 drops. So how many molecules are there, or how many atoms are there inside the atom for which is half filled? Millions and millions, billions and billions. Out of that, you drop only, suppose 2 atoms or 2 molecules is gone, is removed. It does not affect. You did not see any change. So that is the difference. But when there, suppose a glass is there, 5 molecules are there, and out of 5 molecules or 5 atoms, only 1 or 2 atoms are removed, then you can know, you can feel the difference. So that is the difference between classical mechanics and quantum mechanics. So we think both are different, as we cannot perceive quantum mechanics in our day-to-day life. It is counterintuitive. What we feel in our day-to-day life is classical mechanics. But there is no difference between classical mechanics and quantum mechanics. Only for a very large quantum mechanics is felt when we go to the atomic scale. In the atomic level when we go, because for them the quantum numbers are very small. N is equal to 1, 2, 3, 4, and 5, 6. And what in classical mechanics, in our day-to-day life, we are dealing with the particles or molecules with very large number. N is equal to 5 billion, 10 billion. So we are not feeling quantum mechanics, but we feel only quantum mechanics. So that is why in that sense, extending this idea, we extend classical computation to quantum computation in the atomic scale. Similarly, the device of classical computer is now we devise to quantum computer, which works in the atomic scale. Now, what is the need for these quantum computers? Yesterday, professor has told that we are developing integrated chips, and initially, actually, what is a classical computer? What is a classical computer? Classical computer is made up of registers, and register made up of a set of registers, and registers are made up of gates and wires, or not? Gates and wires. But this how gates and wires are physically constructed through the help of the transistor. Initially, when the classical computer was constructed, the first classical computers, it works on 10 to the power 3 flops per second, floating point per second. But now it is coming as 10 to the power 18 flops per second through the help of the transistor. And how they have got, initially it was vacuum tube transistor, but initially they got into the silicon chip transistor, then integrated chips. Then why all this is done? Because I want to increase the computing power of the computer, or I want to decrease the processing time. So when we want to decrease the processing time and computing, when we want to increase the computing power, then what you will do? You will keep the transistor and the gates and the circuits very close to each other, very close. And you see that Moore's law tells us that every 1.5 years, from 18 months to 2 years, the number of transistors which can be integrated chips doubles. In a given single chips, the number of transistors which can be embedded, it doubles in every 2 years. So if you want to increase the computing power more and more, we want to keep the transistor very close to each other. So when you bring the transistor all close to each other, then what happens? You go to the atomic scale, you go to the quantum scale. So once you go to the atomic level or atomic scale, then you will see that classical mechanics will not be valid, because I know that in the atomic scale or quantum, in the atomic scale, the quantum mechanics law is valid. So that is the one of the main idea why we need a quantum computer. The second idea is that reversibility. You must have heard about I told you the quantum computer is made up, any computer, not quantum computer, is made up of set of resistors. And resistors are nothing but a collection of gates and wires. But the gates, most of the gates in your classical computers are not reversible. not reversible in the sense, except for example, NOT gate. In the NOT gate is most probably the only natural reversible gate. And what do you mean by reversible gate? Reversible gate is that gate where you suppose some input is given to you, output you get, and from the output you can predict what is the input, then it is called a reversible gate. So in the your AND gate, NOT gate, one is given, bit, smallest bit of information in classical computation is bits, 1 or 0. If 1 is input, you will get 0 output, 0 input, 1 output. So by looking at the output, you can know what is the input. But this does not, for OR gate or for JOR gate or for AND gate, it does not happen. Suppose you will say the 1001 output, you cannot predict that input was something, a concrete one, a precise one. You cannot predict. So most of the gates in classical computations are irreversible gates. But all the gates in quantum computers are reversible gates. And what is the advantage of this reversible gate? Reversible gate tells me that there will be no heat loss. There will be no heat loss. And what is that heat loss? You must have heard about when one bit of memory is lost in the process, then KT ln2 amount of heat is dissipated in the environment. When either 1 or 0 is erased from the memory of the computer, then K into T into ln2, this much amount of heat is lost to the environment, where K is Boltzmann constant, T is the absolute temperature, and you know what is ln2. And this has been given by, this formula has been derived by, you see, heat loss related with thermodynamics. So this classical information theory is based on your thermodynamics, giving rise to, like you must have heard about classical information theory. You must have heard about Shannon entropy. So all this Shannon entropy, classical information theory is based on your classical thermodynamics. So that is one of the advantage of the quantum computer, that for reversible gate, there is no heat loss. Okay. Like that. So we need quantum computer for our purpose because you are working in the atomic scale or irreversible scale, and another one is your reversibility of the quantum gates, because most of the gates in classical computers are irreversible. So there is heat loss. Then this is something, if you can observe, this is some timeline about the development of your quantum computer. Initially, the physicists gave all these ideas. Then algorithm was developed, like your source algorithm, Grover's algorithm. Okay, then first working qubit quantum computer is constructed. Then like that, and now, for example, 2019 IBM launching its first commercial 20 qubit QC. But in 2023, most probably I have heard that 1000 qubit computer has been developed by either IBM or Microsoft and something like that. Okay. Then this is some brief history which I have written. The language, just go through what quickly. 1981, Feynman was the first man to give ideas about quantum computation. And then Dewey's algorithm, source algorithm was developed. Then quantum bit, a qubit, because I know that smallest bit of information in classical computation is bit, like 0 and 1. But here we have a qubit, which is a linear combination of 0 and 1. But 0 and 1 are not binary numbers, but they are a vector space, some vectors, 0 vector and 1 vector, and like that. And then Grover's algorithm. Then 1998, first quantum computer. 2001, IBM Stanford University published something, 7 qubit processor. Then 2011, first commercially available quantum computer was developed by D-Wave system. Then IonQ is a hardware company who is also produce quantum computer. Now 2020, 21, I have given some histories. Please go through this one. Then these are the some figures of your quantum computers, like your the first one is developed by IonQ, next one is Chinese 76 qubit photon-based quantum computer. Why photon-based? Why 32 qubit quantum computer? I shall tell you in a minute after this slide. And then the third, the right-hand side figure is your IBM 53 qubit superconductor. Now you see a smallest bit of information in your classical computer is 0 and 1. But now here it is a smallest bit of information is a qubit. And what is a qubit? Qubit is actually a vector in a vector space C2. And that vector space is your actually a Hilbert space. Okay, so Hilbert space is also a vector space, but with some like your, it is complete with respect to norm and obeying certain properties. So we shall not go into detail about this one. We shall make use of this only vectors. So how to represent a vector? You see this zero vector, that is cat vector has given by, it is simply 1 0 column vector. And one cat is simply 0 1 your cat vector. So in that way, and how they can be realized? What is this is the mathematical? Okay, why I am giving you mathematics? Because mathematics tells me about a qubit, and I have written a qubit in a mathematical form, like a linear combination of 0 cat plus 1 cat. But how this qubit can be realized? The qubit can be realized in many ways, like your this. If you, I shall tell you in the later what is this 0 vector and 1 vector. 0 vector and 1 vectors are the two state of a two-level quantum system. What is a two-level quantum system? For example, in the hydrogen atom, the ground state and the fast excited state is a two-level quantum system. Second one is, if you take a Josephson junction, which is a superconducting qubit, it constructs a superconducting qubit. Okay. Then third one is the two-level quantum system can be realized in terms of a photon. So what is a photon? Photon, I know that photons are particles or quantas of light, but these photons are actually polarized. You must have heard about polarization. The photons, if it is considered as a wave, the electric field vibrates either vertically, you can imagine, or it vibrates horizontally. So these two states, one is vertical direction vibration and the horizontal direction vibration, both corresponds to 0 and 1. So this is also a two-level quantum system. Then the most common example of a electron spin. A electron, either if this is a electron, then this electron either moves like, it moves around the atom, it moves around the nucleus, that is a different thing. But it also moves around its own axis. If its own axis it moves, it is either clockwise rotation or anti-clockwise rotation. So these are the two states of the electron. Electron can stay either move clockwise about its axis or anti-clockwise about its own axis. So these are the two states. So this a electron can be considered in these two states can be considered as can form a qubit. So we shall not go into detail about the physical realization of a qubit. That is the work of a quantum hardware, or that is the work of your physicists. They are trying how to construct or how to physically realize a qubit. Okay, so that a lot of work is going on that one. But all these qubits can be generalized by mathematics. And that, let it be a electron spin, let it be your ion trap, or let it be a superconducting qubit, or let it be a photonic qubit. All this can be represented by mathematics. So mathematics is the more general language of a qubit. So that is why we shall go into detail about this one. Now you see, now I have a small comparison between your classical computation and quantum computation. That is your conventional bit and a quantum bit. In the conventional bit, it is the smallest unit of information, that is 0 and 1. Bit can take only two values, 0 and 1. But here, the smallest unit of information is your quantum bit or a qubit, and a qubit can take any value, which is a linear combination of this 0 cat and 1 cat. Okay. Then you see, what is the difference between this conventional bit and the quantum bit? The conventional bits are inherently stable. The 0, 1. Suppose in the memory you are keeping 0, 1, 1, 0. There is a very less chance that this will be something different, or that it will be erased, or 0 will convert to 1, or 1 will be converted to 0. Basically less chance unless you apply some external force. But in quantum bits, it changes inherently unstable. So that is called your decoherence property. Decoherence property is another feature of your quantum mechanics. And this decoherence property, it can be rectified by quantum error correction. So that we had a different chapter already, how to do quantum error correction, all these things. But in classical bits, the value of the state of a bit can be determined precisely, hence they are deterministic. You can exactly say the function value deterministic. But in quantum computing, the value or the state of a quantum qubit is always probabilistic. Bits are, and why this concept has come probabilistic and deterministic, because it is dual in nature. In quantum mechanics, I say that everything is dual in nature. Dual in nature means what? A particle can behave as a wave. You must have heard about wave function. What is wave function? Wave function psi is a function of position and time. But what is the physical meaning of psi? Psi has no meaning. Suppose I am walking along the road. I am a wave, so I will be associated with a wave function. But wave function is what? A function which depends on position as well as time. But what is the physical meaning of wave function? Wave function has no physical meaning. But wave function mod psi square has a meaning. So what is psi? Mod square is the probability of finding me at particular position x and time. So that is where this probability concept has come, that the quantum computation uses the widely used of this probability nature. Then bits are physically implemented through electronic or optical devices. Like your bits are either switch can be on or switch can be off. But quantum bits are, you see, implemented by using quantum system like trap ions or atoms or superconductors. Now you see, this gives a figure. A conventional bit, you see, it uses a transistor circuit which uses a switch like on and off. Okay. But you see in the light side qubit, how it is by through the Josephson junction. Josephson junction is something related to superconductor, where the current can be controlled by your superconducting devices. You must have heard about superconducting devices. What are the superconductors? Superconductors are the things which shows zero resistance at some temperature. So the qubit relation can be either by superconducting qubit or ion traps. So how the qubit can be realized? You take a silicon chip, silicon chip, and in the silicon format you constant some ions kept inside some box, some like structure, and that ions can be controlled, whether to go from this box to that box to go back. That is called ion trap. I am not going to detail about the physical realization of this one, but I say that the qubit can be realized by, so just like bits are realized by switching on and off through the help of the transistor. Similarly, the qubit can be realized through Josephson junction from like your superconducting qubit, ion trap, quantum dot, and photonic device, etc. Then the quantum mechanics, the quantum computation makes use of this superposition. Superposition you have heard about. Already I have told you the qubit is written as a linear combination of A of 0 plus B of 1, where A and B are complex number, but these 0 and 1 are two states. So it is a linear combination of two states. That property is called your superposition. But this 0 and 1, these are special type of states which are orthonormal states, or they are called orthonormal basis vector in a vector. I know that if there is a vector space, this vector space can be described by some basis vectors, and that basis vectors they obey orthonormal basis. I shall tell in a minute. I shall tell you what is a orthogonal. What do you mean by orthonormal basis? What do you mean by orthogonal vectors? And what do you mean by normalized vector? But these 0 and 1 are actually orthonormal basis. So a linear combination of this is called your superposition. Then it is also associated with entanglement. And entanglement, what is that one? Actually, in classical mechanics, suppose I say that there are two particles. The two particles, particle 1 and particle 2, they come together. Okay, there may be some force acting between them. Suppose these are charged particles. So there may be some force acting. Suppose there are only masses, no charges. So there can be gravitational force. But when these particles are here, they will interact with each other. But now when you take it from infinity, if you take a very large distance, absolutely the properties of this particle and the properties of these particles are actually, there is no absolute difference between, there is no absolute connection between this one. As they are together, there is some interaction, but when you take one particle away from other, the properties of this does not affect the properties of this particle. But in quantum mechanics, it does not happen. In quantum mechanics, if the two particles are coming together, they will interact. And if you take this particle up to infinity also, there is some linkage between this particle and this particle. If you do something here, then there will be change in that particle also. That is called your entanglement. So this entanglement superposition, I want to explain you in mathematical, not through physics. Okay, because the computer will understand the mathematical language. Like your classical computer obeys the binary logic or Boolean algebra. Similarly, quantum computer obeys your linear algebra of Hilbert's. Then another advantage of qubit you see, the adding qubits increases storage exponentially. Just like you see to the digital computer, suppose a classical computer, I have 32 bits. Suppose I want to double its power, then I have to meet it 64 bits. But in quantum computer, if 32 qubit quantum computer is there, and I make it 33 qubit, only by increasing by 1 qubit, the power of the quantum computer will be doubled. So just by increasing only 1 qubit, I can increase the power of the quantum computer. Okay, the second advantage is that a 64-bit computer can perform manipulation on 64-bit binary numbers at a time. But a 64-qubit quantum computer operates in a space of 264 dimensions, or roughly 16 into 10 to the power 8 numbers to specify the state of the quantum system. So these are the advantages of the qubit. And what is the advantage of actually quantum computer? Why we need this quantum computation? It also deals with computational complexity. What is the computational complexity? For example, suppose I want to determine whether a number is even or odd. P is a 6-digit number or 10-digit number or a 9-digit number. What will be my complexity? My computing power of the computer should remain same. It will take same time. With respect to time, I am talking. Computational complexity with respect to time, I am talking about. It will take same time to check a even number or whether a number is even or odd of anything, or it will take more or less time. With respect to time. For example, you take any number, a 100-digit number, or a 6-digit number, or a 2-digit number. Suppose I want to check the whether it is a even or odd number, then what I have to check? I have to check on the last digit. So for any number, I have to check the last digit. So my complexity in time is constant. That is called constant time complexity. Suppose I want to add two numbers. And if I add two numbers of 2 digit only, and then I increase to 3 digit number or 4 digit number, what will happen? My complexity, my time will increase or decrease? It will increase. If you add two big numbers, then it will take naturally two. So in that way, the time increases with the time linearly. So it is called linear time complexity. Suppose I have a I want to decipher my PIN number. PIN number I have, suppose two unknown number. I have to put two PIN, then I will get my things in OTP. So what are two numbers? So how many numbers I have to put to check whether one will be correct? Either 0, 0, 0, 1, 1, 0, 1, 2, or 3, 4, 9, 8. So it is 10 to the power 2. Suppose I want to 3 OTP, 3-digit OTP. It will be 10 to the power 3. Suppose 4-digit OTP, 10 to the power 4 times I have to sum. So in this way, the complexity time increases logarithmically. So it is logarithmic time complexity. So similarly, we have quadratic time complexity. We have exponential time complexity. So there are some problems like your quantum mechanical problem in your atomic scale many body system, okay, or in biological system where we require, if a classical computer will try to solve that problem, that type of problem, it will take exponential time or it cannot solve. For example, the source algorithm, how it was developed. Suppose in the cryptography make uses of the prime factorization problem. If there is a prime number, then I want to, suppose there is a very large number, I want to factorize into prime numbers, then I have to make some formula or not. I have to develop some algorithm. So till now, all the cryptography in this world is based on this prime factorization problem. And prime factorization problem tells me that if there is a very large number, composite number, you cannot, very, very large number, it will take exponential time. 10 years, 100 years, maybe 5,000 years to factorize it into prime factors. But source algorithm has developed basing on the quantum algorithm where any composite number can be prime factorized. So that is one of the main application of your quantum computation where all the Vodafone, etc., they are now cryptography, image processing, they are doing this. So they are basing on that, how to develop quantum cryptography. So that once quantum computer will be developed, they will remove all the cryptography problems of your classical one. Then how to stop that one? So they are developing quantum cryptography, Vodafone, image processing. So like that. So quantum computer cannot replace the classical computer. Quantum computers will somehow solve so many problems which cannot be solved by your classical computer. For example, new drug discovery problem. In the biological system, new drugs are coming out. How to develop? So that problem. Second one is financial problem. Financial market, ups and downs. You know that all these are based on some equation called Black-Scholes equation. So all these Black-Scholes equations, stock market up and down, are actually nothing but Schrodinger equation or one-dimensional heat equation. So that can be solved with the help of quantum computer. So like that, quantum computer is not a replacement for classical computers. It can solve many problems in many areas which classical computers cannot do, and more efficiently with less time. That's all. Okay, so just like I have told you. Now, before this, I shall state only one line. Just like your I have told you for all quantum mechanics, for large quantum number, quantum mechanics will become classical mechanics. Similarly, the quantum gates we shall develop for quantum computer. All quantum gates are superset of all classical gates. Classical gates are finite in number, many gates are there, but quantum gates are more in number compared to classical gates. And all the classical gates can be realized in terms of quantum gates. So basing on this, now let us start with the representation of a qubit. So what is a QC? A quantum bit is a linear combination of vectors 0 and 1 in C2, where C2 is a Hilbert space, and a qubit is represented by A of 0 plus B of 1, where A square plus B mod of A square plus mod of B square is equal to 1, and A, B are actually complex number. Why this mod of A square and mod of B square? I can say that because psi is a wave, these A and B are actually, these are probability amplitude. Okay, and probability amplitude mod square is the probability. And I know that probability of an event, the sum of the probability of an event is always equal to 1. So that is why mod A square plus mod B square is equal to 1. Okay. Then the same qubit also can be represented by in complex number. That is mod of psi is equal to R1 0 plus R2 into e to the power of phi I 1. Where you know that R1 and R2 are something like you have written in a complex number. What is the mathematical formula of a complex number? A plus IB. A plus IB, where A and B are number, I is a unit number. So similarly, exactly, it has been represented by this R1 of 0 plus R2 of e to the power phi I, and this obeys this condition. R1 plus R2 square is 0. Phi goes from 0 to 2 pi, and theta goes from 0 to pi. And R1 also can be represented by cos theta 2, R2 is equal to sin theta 2. So naturally, the qubit can be represented by cos theta by 2 by 0 plus sin theta by 2, e phi I is equal to 1. So now I shall define what is quantum computation. A quantum computation is composed of three elements. That is a register or set of registers, a unitary matrix U, and why unitary matrix I shall tell you within a minute. A unitary matrix U which is tailored to execute a given quantum algorithm, and measurement to extract information we need. So actually out of these three quantum computers, the first one is, you see, a register or a set of register. And I know what is a register. A collection of wire and gates. That is, along with instrumentation for controlling qubit, forms a quantum computer. So that part is your hardware. A register or a set of register along with some instrumentation which controls the qubit, together they forms a quantum computer hardware. And the second one, a unitary matrix U and measurement, these are associated with your software of the quantum computer. Now, quantum mechanics, I shall tell you. I have already told you that in quantum mechanics, the particle behavior or a wave behavior can be described by not by Newton's law, by a Schrödinger equation. Now you see what is a Schrödinger equation. Schrödinger equation is I h cross d by dt psi t is equal to h t psi t. You know what is psi t? What is psi t? A wave function, and for the timing you can imagine it is a qubit. Psi t is a qubit. And h cross is a Planck's constant associated with some physics. I is your imaginary number, that is minus 1 to the power square root. And left hand side is derivative of psi t, wave function with respect to t. That means the wave function changes with time. From that, I know that wave function changes with time because psi is a function of t. And right hand side is the energy or Hamiltonian h, which is a function of t and psi t. Now, solution of this equation you closely observe in the last step. In the last step, what you see there, psi t is equal to u into psi t0. You have observed or not? What is the last mathematics? Last line of mathematics. Psi t is equal to u into psi t0. What is psi t0? The value of the wave function at initial time. And what is psi t? The value of the function at time t. So how to get from psi t0 to psi t? How to know the value of psi t? Psi 2 value can be known from psi t0. Psi t0 value is known, initial value is given to you. Then u is acts on it. U is something which acts on it. Now a mathematical term, a unitary matrix. A unitary matrix acts on it so that you get a new state. So that you get a new state. Now I am doing for classical computation. Suppose I have my information is either 0 or 1. Let psi t0 be 0. 0 to I go to either 0. What is the change from 0, 1? 0 can go to 1, 0 can go to 0, 1 can go to 0, 1 can go to 0, something like this one. So there will be interchange between 0 and 1. So in the binary logic, in the classical computer, you go from 0 to 1 by some operation. What is that operation? Who does that operation? Achha, I'm asking you another simple question. Suppose in the classical computer, the information is stored where? Information is stored in terms of what? 0 and 1. The information is stored in the computer let it be a number, let it be an image, let it be something else. Everything is stored in the form of 0 and 1. Then you do some logic on you apply classical algorithm. What is the classical algorithm? Some set of instruction. You apply the classical algorithm so that this information will be modified and you get a new thing or not. So information is stored in the computer, then in the memory, then gate acts on it, indirectly this gate acts on it, and you get a new state of 0 and 1, a combination of 0 and 1. Similarly, here also you have a qubit, psi t0 initial qubit, and this u acts on it so that you get a new state psi t. So in these three mathematical terms, psi t0, u t, t0, who is playing the role of a gate? U. U is playing the role of a gate. So that is the quantum gate. Okay, so u t0 will play the unit, and we shall see that u is actually a unitary matrix. What is a unitary matrix? What is a Hermitian matrix? I shall tell. But in quantum mechanics, you see in classical mechanics, I want to observe something. I want to measure suppose position or momentum or a charge of a particle. And then how do I measure this one? By some instrument or not? Suppose a particle is moving with some velocity. I measure it. It is 5 meters per second by some speedometer. I measure it is 5 meters per second. Then again it is going, I shall measure by speedometer. It will be suppose 3 meters per second. I shall measure it. Suppose it is 2 meters per second. So the particle is moving, is going in its way. I am measuring the velocity, I am measuring its velocity by some instrument. But this instrument and my particle all are independent of each other. It is not affecting this one. This is also not affecting this one. So in classical mechanics, the observed thing, observed quantity, and the instrument by which you are measuring, it is not disturbing the system. It is not disturbing the system. But in quantum mechanics, it does not happen so. For example, in ordinary sense also, suppose I have a temperature and I want to put thermometer here or in my mouth. Okay. So what will it will tell that it is 100 degrees centigrade or 200 degrees centigrade. Oh, sorry, not 200, 100 degree Fahrenheit or 104.8, something like that he will tell. So I assume that the temperature of this body is 100.2, something like that. But it is not true. When you put the thermometer inside my body, actually this thermometer is taking some heat from my body, and then the mercury is expanding. So indirectly, by inserting a thermometer in my body, actually you are lowering my temperature. But it is not so much in classical mechanics, because this loss of heat is very, very less. But if you go to the atomic scale, because the energy is so less, if you take a very, very minute amount of heat also in it, this will affect my observed quantity. So that is taken into account in quantum mechanics, which is not taken into account in classical mechanics. And for that, I have some mathematics. So that mathematics is your postulate 2. Now you see what is postulate 2. Any physical observable A is associated with a self-adjoint operator. I shall understand what is meant by self-adjoint. And on the Hilbert space, the possible outcome of a measurement of a observable is one of the eigenvalue of the operator A. Writing the eigenvalue equation. Eigenvalue equation, you know, some mathematics, computer science student, everybody should have known. What is the eigenvalue equation? A is an operator. Operator A acts on a vector, and this is equal to some eigenvalue, which is a scalar number, into the eigenvector. So I's cat is called eigenvector. A is an operator, and AI are the eigenvalue. Okay, and the wave function psi t is given by linear combination of this eigenvector, that is CIT I summation. So that is why probability is your I psi t is equal to CIT by whole square. So this mathematics. Okay, I am not don't go detail about this one. I am just telling you this is the postulates of quantum mechanics. I shall till now more fundamental is left for you. I shall start from a basic vector. Okay, so don't go about this one. Just I want to tell you now. You see the postulate number 3. Postulate number 3, that if a system is described by the wave vector psi and we measure an observable A, obtaining the outcome An, then immediately after the measurement, the state of the system is given by Pn psi by psi Pn psi square root. Some notation, some mathematical notation. So initially, before measurement, it was only psi, but after measurement, you have disturbed the system. Then the new state of the system is the new mathematical formula, the last one. Okay, so measurement also plays a role in this one. So now you have gone through all these things. Some notation, some odd notations are there. So these notation I am making you clear in my next talk. And here some figure I have given you. Now you see measurement. How measurement related with quantum computer or a qubit. Okay, now you see that a qubit, what is a qubit? Qubit is equal to psi is equal to alpha of 0 plus beta of 1, where 0 and 1 are the two vectors in the Hilbert space, vector space, and alpha and beta are complex number. This is a qubit. But when you measure it, it will not be 0 and 1. It will be either 0 or it will be 1. So it will measure as 0 with probability mod alpha square, and it will measure 1 with probability mod beta square. So this is a very typical character of your measurement. Initially the state was alpha 0 plus beta 1. But when you measure it, it becomes either 0 or it becomes. Got my point? No. Very difficult. So I am telling. And this is measurement operator. Now don't go into detail about this one. It has some notation like bra and cat notation. So there is some expectation value. So now I shall start. Now you see this is now Stern-Gerlach experiment I shall explain, and after that I shall start your basic mathematics of this one. What is the time left? Only 1 hour gone. Oh, very good. Now you see the Stern-Gerlach experiment. You closely observe. What is this Stern-Gerlach experiment? suppose you have an atom, silver atoms are produced, and these silver atoms are made to pass through horizontally like this. Now, when this silver atom is passed through a magnet, okay, and this magnet is a inhomogeneous magnet, like you have North Pole and South Pole, somehow make this North Pole stronger or South Pole stronger and make the other pole little weaker. So it is not a uniform magnet, but a magnet of producing a inhomogeneous magnetic field. One pole is stronger, one pole is little weaker. So if the beam of silver atoms are made to pass through it, then and if you put a screen on the other side, you will see a figure something like this one. You will see a figure. One loop you will get something up and something down, a discrete phenomenon. But so why do we get this one? Because silver atoms or electrons are moving around the nucleus. Okay. Also, suppose it is around the nucleus, suppose nucleus is there, so electron will move like this one. The electron can move like this one. All the probability is having figure. So if they figure, so if you have a electrons are moving like this one, orbital motion, their actually angular momentum will be given either upward direction anti-clockwise, or maybe if they are moving like clockwise, I can give downward direction. So I have any possible direction. So what should figure you will get? You should have got B is not equal to 0 classical prediction, like that figure you have got, because your electron can move in any direction. So you have got a continuous figure, but you are not getting that one. You are getting this up and down. B not equal to experimental result you are getting, you see. So why it is happening? That means first thing is sure that yesterday Professor Panigrave I was hearing, he also told that this type of angular momentum, it does not play any role. But the electrons which are there, the electron can either move in, the electrons are either can move in spin up direction or spin down. So due to this spin up and spin down, the net force on the electron is different. For spin up some force, for spin down some other force in the opposite direction. So that is why you are getting splitting of this. Okay. So now you imagine. So now this argument finishes here. Now the electrons are moving. It is separated into two parts. One part moving upward, one part moving downward. Suppose I take another magnet, exactly same magnet in the same direction. Same magnet in the same direction. I will measure. I will get only one strip. But if I keep another magnet perpendicular to it, again I shall get a two strip. So this means that measurement, whether I will get one strip or you listen or diverted somewhere. So this is one magnetic field. It has split into two parts, one part and another part, up and down. Suppose I put a similar magnet exactly keeping parallel to the first magnet, I will get in the path of suppose up one, I shall get the same figure. But if I keep a magnet in the perpendicular to it, I shall get again two strip in the horizontal direction. Suppose these are a screen here and here I have got, then I will get a split in this direction and this direction. So what the result you are getting, it is depending upon the measurement by which you are taking the measurement. Either in this direction or in this direction you are taking the measurement. So the measurement plays a role in quantum mechanics. That one and that is why we need mathematics and we need measurement operator, and I have told you all this. Now you see, now just this is a comparison. Now suppose you have 4-bit computers. 4-bit computers you have. So how many possibilities are there? 16 possible states. 0, 0, 0, 0, 0, 0, 1. There are 16 possible states. But the classical computer will act one after another. First this state, then second state, then third state, then fourth state. But in quantum computer, all the 16 states will be analyzed once. So that is called your quantum parallelism. Now I take a break for 2 minutes. Then I shall start with the more basic one. Okay, I want to make acquainted with your vector algebra. That is your bra and cat notation you have heard. What is a bra and cat? Just take 1 minute gap and then I shall tell you the basic of this bra and cat notation and basic mathematics of this quantum computers. Now let us come to pure mathematics of quantum computation. Now you see from the figure, now it is very easy. Now you see what is your alpha A cat. A cat what I have written? 3, 2, a column, right? A column vector. A column vector is represented by a vertical line. A row vector will be written as a horizontal one. And what is the, if you consider this is a matrix, what is the order of the matrix of A? 2:1, 2 into 1. And similarly for B also. Now I can represent this vector A and B in my graph like this one. Now you see addition, how I have got. Now you see addition. A plus B is equal to C. C will be what? Just 3/2 plus 1 minus 2 is equal to 4/0. So in the figure, I can guess what is 4/0. Now you see what is the scalar multiplication. Suppose the vector B is 1 minus 2. 1 minus 2 is multiplied 2 times. So 2 into B will be 2 and minus 4. So how 2 minus 4 looks like? Similarly, a linear combination. Suppose I have a vector 3, 2. I have a vector 1 minus 2 or A plus B. So 2A plus 3B is equal to 6/4 plus 2 minus 4 is equal to 80. So how 80 will look like? So this is just a graphical representation of addition, scalar multiplication and linear combination of vectors that we know already, but just I am acquainted with your cat notation. Okay. Now you see a bra and cat notation. What is a column vector? Already I have known what is a cat notation, A1, A2, A1, and what is the row vector? That is your bra notation, Y. Y is equal to row vector A1, A2, An. Okay. Suppose now I want to multiply these two vectors. These two vectors or matrix can be multiplied or not? What is the order of the matrix of a column vector in the figure? N is to 1. And what is the row vector? It is 1 is to n. So A is n into 1 into 1 into, and this can be multiplied. So now X and Y are multiplied. You see the notation. Just I am telling you the notation that's. Now X and Y, how I have written X, Y bracket or not. It is given by X1, X2 row vector, Y1, Y2 row vector. This is X1, Y1, X2, Y2, X3, Y3, something. Now just go to the next line. Matrix representation. How to write down the matrix representation? Suppose a matrix A is there. So just write down the first row as R1, first row as R2. Sorry, second row as R2. Third row is your Rn. And now you multiply a matrix into a vector, A into X. Last line, A into X. So A is written as R1, R2, R3 in the bra notation. Now multiply with x. X is what? X1, X2, A1, A2, A3, A and something like this one. Now multiply, you see the result. Ax is equal to y and y will be equal to R1x, R2x, Rnx in this Bryant cat notation. Which is difficult to remember ordinarily, but it is very easy to remember in the Bryant cat notation. Now you see the next line, matrix multiplication, how matrix multiplication how will do? A is equal to this one. Then I have converted into R1, R2 and R3. Then X is equal to WYZ. So what is AX? AX is equal to 432, 413, 242, WYZ. And that is equal to 4W plus 3Y plus 2Z, 4W plus 1Y plus 3Z, 2W plus 4Y plus 2Z. And that is equal to, in Bryant cat notation, I can write down this one R1X, R2X, R3. That's A dot B is equal to now issue. Suppose A, this is a matrix multiplication with a vector. This is a matrix multiplication with a vector. But now the next line you see, if A is a matrix, B is also a matrix, then how to write out this? R1C1, R2, R1C2, R1C3, R2C1, R2C2, and R3C3. Just like you have divided A into R1, R2, R3. Similarly, B should be divided into column 1, C1, C2, C3, like this. And just you have a matrix multiplication. Now we shall understand some terminology. For example, inner product. Now just see what is the inner product. That previous notation we have used, that can be used for the defining inner product. Suppose X is a vector, Y is a vector, X cat and Y cat are two vectors, then the inner product between the two vectors will be something like your X bra and Y cat. So this is XY and it is given by that formula. And by a mathematical formula, you have this one. Just I have simple example. If X is equal to this one, Y is equal to this one, then YX is equal to how 2y3 into 3y2 is equal to last result is 5 plus 6i. Similarly, you see what is XY. So in general, XY is not equal to YX. XY is not equal to YX. For the first case, it was 5 plus 6i, but now I got 5 minus 6i. Then what do you mean norm of a vector? Norm of a vector is this one, x mod is equal to xx square root. So suppose I have a x is equal to 2, 3, 4, then norm is equal to 29 square. Suppose normalization. What is normalization? You divide it by norm, then it will be a vector of unit length. So that can be used by just simply I am writing down in the Bryant cat notation. That's all. Then orthonormal vectors. Orthonormal has orthogonality as well as normalization. If the inner product xy is equal to 0, they are orthogonal. If it is normalized, then norm of x is equal to 1. So, for example, check of orthonormal basis vector, if I am giving 0 and 1, you see 0 is represented as 1, 0, 1 is represented as 0 and 1. Then it is 0, 0 is equal to 1, 1, 1 is equal to 1, 0, 1 is equal to 0, 1, 0 is equal to 0. So mathematically, I write Ij is equal to delta Ij for orthonormal vector. Then we shall make use of one principle called ground speed process. Suppose in the vector space we require an orthonormal basis. Suppose, but my original basis is not a orthonormal basis. So then some mathematical algebraic manipulation is there to construct a orthonormal basis from a non-orthonormal basis or any random basis. That is called your ground speed process, that you know. That I am not doing it. Then this is something new. I don't know whether you have or not. Outer product of two matrices. Now you see what is the notation. Previously in the inner product, what was there? Brand, it was something like this one, U and V, but now you see the opposite one, U cat into V bra. Okay, and that is with this notation, U1 V1 star. means complex conjugate. Okay, V vector has V1, V2, V3, V4, something like this one. So complex conjugate of that one is V1 star. So you apply that one. For example, an example has been considered. U is equal to 3, 2, minus 1. V is equal to 7, 2, 3, 1. All the numbers are real. So there is no change in the star notation. So it is 3, 2, minus 1, 7, 2, 3, 1. It is multiplied to, you see, U is a what? It is a U cat is a 3 cross 1 matrix. And V is also a 4 cross 1 matrix. But outer product of the matrix is 3 into 4. See, it is not normal matrix multiplication. It is outer product of two matrices. Then some matrices which are more frequently used in quantum gates or your quantum computation, these are called polymatrices. Polymatrices are rho x, rho y, and rho z. This rho x, rho y, rho z are, you see, 2 cross 2 matrices, but they can be written as the outer product of this 0 and 1 vector, 0 vector and 1 vector. So this is an example how a matrices can be expressed as a outer product of two smaller vectors. Now you see there is another type of product called your tensor product, which is we shall make frequently used in your entanglement. When we study entanglement of matrix to quantum system, then that we can make use of this type of product that is called your tensor product. You see, x is again a cat vector, y is again a cat vector, like your x1, x2, xh, and it is y1, y2, yk. But now if you found out a tensor product between these two vectors, then the product is something like this one: x1, y1, x1, y2, x3, y1, and similarly xh, y2, something like this. Now you see in the figure example, and most probably here it is tensor product is where h is equal to k. Here h is equal to k is shown. But you can, if h is not equal to k also, you can write down the tensor product between the two vectors. And 0, 0 tensor product is given, which we shall frequently make use in quantum gates. That is 0 vector is equal to, sometimes it is 0, 0 in one notation, and 1, 0 tensor product into 1, 0 is equal to 1, 0, 0, 0, 1 is equal to 0, 1, 0, 0. Just see what is the tensor product between the two vectors. So tensor product between the two matrices, you see, but this is the formula in general. A tensor product into B is equal to A11, A1n, AM1, A1, it is multiplied with the whole matrix B. Okay, you see in the example you given 1, 1, 3, 4, tensor product into 0, 5, 6, 0. So you 1 multiply with matrix B. Again, in the next matrix, 1 is again multiply with the matrix this one. Then 3 multiply with the matrix B. Again, 4 is multiply with the matrix B. And the net result is this one. Got my point? This one understood tensor product? Okay. Now types of linear operator we shall make use of. This is quantum gate. In the quantum gate, what you have used? You see, not quantum gate. I am telling you this unitary matrix acts as a gate. And what is the function of the gate? It takes a 1 qubit state psi t0 to psi t. I told you that one. So U is actually a matrix. And I know that a matrix can be regarded as an operator. Any linear operator. What is a linear operator? What is a linear operator? Linear operator is a operator which acts on a vector which gives rise to a new vector. Okay, operator is something in a rough language, it operates on a vector giving a new vector. So a old qubit is converted into a new qubit through the help of an operator, and that operator is nothing but your quantum gate. And operators can be represented by a matrix. Operator can be represented by a matrix. And a quantum operator, more specifically, it is a unitary matrix. It is a unitary matrix, and it is a linear operator. So these are the properties of the linear operator. Okay, it acts linearly on two vectors and has some property. Then enter कर दो. I can see. That's what page down, no? Yeah, page down. I do something. All computer science students are there. Huh? कैसा? आ जाओ आ जाओ.
सामने इसका
हाँ, correct. No, but it is not moving, ना? नहीं, इतने की जरूरत नहीं. नहीं, उसको नॉर्मल कर दो. ये फुल स्क्रीन है ना, इसको हाफ स्क्रीन. हाँ. हाँ? Will manage? It is visible, ना? No, now it is not changing. Now it is not changing. Okay. Now sound is coming, I think. Okay. So this is the types of linear operators, and then we have sound is coming. It is not coming. No, not coming. Let me. Huh? ठीक है ठीक है कुछ मैं करता हूँ ठीक है हाँ, नहीं, now I So now again go to we have understood what is a linear operator. Linear operator, then I say that this linear operator can be a normal operator. A normal operator is what? A dagger is equal to A dagger A. And what is this A dagger? It is adjoint. Adjoint of the matrix A. And I believe everybody understood what is adjoint of a matrix. Row will be changed to column and it will be complex conjugate. Okay, then it is called an adjoint of a matrix. So A adjoint is equal to adjoint A. Then it is called a normal operator. Then I have a Hermitian operator. And Hermitian operator are A is equal to A adjoint. You know what is the eigenvalue of the Hermitian operator? Anybody know? Suppose A is an Hermitian operator. What is its eigenvalue? Real number. So similarly, I have a unitary operator. And unitary operator, the inverse of the operator, if it is adjoint, then it is called a unitary operator. Then I have a projection operator. So projection operator, because in the measurement of your in the quantum computation, we use again, and I told you if for measurement we require an operator or a matrix, and that is type of operator or a matrix is called a projection operator. And what is projection operator? You see a cube is there, you see. Now if you project light from the upside, then what will be the shadow will be formed like this one, a square. Now you see again, if you put the light on the shadow, what figure you will get? Again a shadow, 2 dimension. Previously it was 3 dimension. Then projected from upward, you get a shadow in the 2 dimension. Again you put the light on it, so it will be again same figure you will get. So that is why that projection operator satisfy p square is equal to p. There is no further change. Similarly, for example, a circle, and circle, if you project light from the upside, then what you will get? You will get a line. But when you put the light on the line, again you will get the same line. So this type of operator geometrically is called a projective geometry. But all this operator, that means something is operating on the cube and you are getting a new thing, and that is why that thing is called your operator. And this type of projector is called a projection operator. And I know that operator can be represented by a matrix. So I have a projection matrix or projection operator which can be represented by a matrix. And for a qubit state, the projection operator is given by this one. You see, P is equal to get psi into bra psi, or a P projection operator is also Hermitian. And I have a positive operator definition. With the help of the bra and cat notation, I can define a positive definite operator or a positive semi-definite operator. Then a qubit, which is your A0 plus B1, also can represented by this a block square representation, which is given by cos theta by 2 0 plus sin theta by 2 e phi I1. Already I have told you about this one. For phi goes from 0 to 2 pi and theta measure from theta measure from 0 to pi and phi goes from 0 to 2 pi. This is your block sphere representation. Next. Then in the block sphere representation, you see in the red dot is there. That is called your north pole. And exactly in the opposite direction, in the right hand side figure, that point is your south pole. So this geometrically, if you join a line from the center of the sphere to that red line, that will be your zero vector in the left hand side. And if you join a line from the center to this point on the sphere on the south pole in the lower direction, that is your one vector. So this is called your block sphere representation. And now you see your qubit can be represented by something your alpha 0 plus beta 1. Okay. Now then how qubit will be represented in the block sphere? Because 0 and 1 are the orthonormal basis. Out of this orthonormal basis, you are constructing any arbitrary basis of the qubit, that is alpha 0 plus beta 1. Alpha beta can be any complex number. If you take different value of this alpha beta, then this qubit can be represented by any point on the block sphere. Any point of the block sphere. Then this basis 0 and 1 is called a computational basis. But this is not the only basis. I have other types of basis also. That is, one is called Hadamard basis, one is called your circular basis. Now you see basis 2. Basis 2 is represented by the points you see where it is. Okay, the red points. The red points on the block sphere on the left hand side and the right hand side. The next one, basis 3. I have, you see, closely observe where the dots points are there. So that will represent a basis called circular basis. So I have a formula something like this one. So basis after basis 3. Now the different basis of the block sphere where qubit can be represented either by in terms of 0 and 1, or can be plus minus, or can be I and minus I. So I have a computational basis, I have a Hadamard basis, I have a circular basis, and they are represented by in the axis name is Z, X, and Y. Now, what are quantum gates? Just I have told you, quantum gates are logic gates are analogous to classical logic gates. These are building blocks of quantum computer circuits, just like your classical logic gates and for digital circuits. Every gate operation is represented by unitary matrix. I know now. And the number of qubits in the input and output of the gate must be equal. That is why it has to be a reversible gate. And unlike many classical logic gates, quantum gates are reversible. Okay. But where I want to tell you that when I use of quantum computation, just like your classical computation, I have many methods. Just like first method, my abstract computation, suppose I will do. So I will take the help of a abstract computer. What is the abstract computer in classical computation? Turing machine, Turing, Turing machine, you know, classical Turing machine. So that is the abstract machine which have a control, which have a tap, which has a write and read head. So I can do all the mathematics in this classical Turing machine. Then I have a theorem that is called Church-Turing thesis. What is that Church-Turing thesis? That is that all the functions which are computable in the Turing machine are also computable by any classical computer. Okay. And then I have a classical computation. I have a theorem. I have a machine called your probabilistic Turing machine. So similarly, it has been extended to the quantum Turing machine, quantum Church-Turing hypothesis, and so on. But for doing the practical calculation or practical designing a quantum computer, the most easiest one is your circuit model of computation. So just like where we use the circuit model of classical computation, I shall make use of quantum circuit model of circuit model of quantum computation, and that will be represented by your gates and resistors. Now, in order to go to the gates, I shall consider what are the properties of the unitary matrix. That these already I have learned. Next. Now you see the types of quantum gates. Just like your classical gate, like your AND gate is a one input, one output. But what about OR gate? OR gate, 2 input and 1 output. So that is why it is not a reversible gate. Okay. So similarly, I have in classical gates one input gate. Similarly, here also I have 1 qubit gate or 2 qubit gate. I have a 3 qubit gate. So types of quantum gates can be a single qubit quantum gates, like how it is represented just you see, and can be a multiple qubit gate. And what are the examples of like 1 qubit gate? You have an example in classical gates in classical computation. Uh, what? Your NOT gate, no? And two where there will be 2 input and a gate or a gate. Okay. Similarly, you have control NOT gate, C NOT gate, or not? You have Fredkin gate. Have you heard about fan out gate? Fan out gate, ERAS gate. Okay, out of all these gates, you tell me what are the more universal gate? From those gates, you can construct all other gates. NAND gate is one of the universal gate. From the NAND gate, you can construct AND or JOR any gate. Similarly, a combination of your CNOT gate and fan out gate. They also from that you can construct all the gates. So there are not a unique universal set of gates, but there are many universal set of gates are there from which you can construct other gates. Similarly, here also I have many types of gates: poly gates, Hadamard gate, phase shifter gates, swap gate, control gate, Toffoli gate, Fredkin gate. But remember, here my choice is very large in the quantum gate. Why? Quantum gate, because you take a block square representation, you take it. And how does qubit, a single qubit gate I am talking about. In the block square representation, I put all my information in the 0 vector. That means on the north pole. Okay, just imagine geometrical figure. Then I apply some algorithm. What is the algorithm? What is the function of the algorithm? Algorithm is nothing but through it will be implemented through the gates. So gates will act on it. And it will take from this state to new state. So it will go from this point to another point. So set of algorithm, a set of instruction is given to you on the block sphere. One point, it will move from due to according to my operation, it will act on different point. Finally, it will stay at some point. Okay, and from that you measure it. Okay, through the measurement operator. So this is my working of a qubit through the block sphere representation I am telling you. And physically how it is implemented, I have told you that qubit is nothing but a combination of 0 and 1, and 0 and 1 how will be represented by the spin up or spin down. For example, electron spin up or electron spin down. When you apply a magnetic field, the spin direction changes. So how do you, and this set of algorithm is implemented through magnetic field. This magnetic, you apply, like you set of instruction is given to the magnetic field. This magnetic field will, according to the set of instruction, it will move. And so the direction of the magnetic field on the qubit will change. And according to that, control will be there. And it will at a certain point. So that is your final state of the qubit. That is your final result, which can be measured to your measurement. So these are the gates. Next. It is not. So now you see representation of different gates, like your X gate, Y gate, Z gate, H gate, S gate, T gate, then control NOT gate, control Z gate, then swap gate, then Toffoli gate. It is coming to the screen. Yeah, ठीक है, यहाँ पे नहीं, ठीक है, okay. So now I shall read here. Next. Now we shall go into detail about this one. But it is taking that one. But don't worry. A screen is changing. So this is visible. This is visible or not? Okay, let us continue. So let I shall make them. You can see, na? So I shall teach you. What to do. Yes, sir. Change करिए. Now you see what is a polygate. Polygate takes 0 to 1 and 1 to 0. And I have told you that any gate can be represented by a matrix. So that matrix is 0, 1, 1, 0. And this is a unitary matrix. Circuit diagram, it is written as X something like this one, circuit representation. Then you see, when you apply X on 0, then it becomes 0, 1, and it becomes equal to 1. And 1 goes to 0. Then tell me, what is this gate? Classically, what is the classical analog of this gate? NOT gate. In the NOT gate, 0 goes to 1, 1 goes to 0. So this is the quantum analog of your classical NOT gate. But very interesting thing is that
Sir, we couldn't get anything. We are not able to hear.
We're reconnecting again. Wait, please wait.
So we are discussing about the types of quantum gate. Already we have discussed about what is a single qubit gate and what is a multiple qubit gate. Then these are the different types of quantum gates associated with your quantum computation. And then we have also discussed about in detail what is a poly X gate. And this poly X gate actually, it is the classical analog. Its classical analog is your NOT gate. NOT gate does the same operations like your poly X gate. But besides that gate, I have a poly Z gate. The Z gate 0 to 0, 1 goes to -1. Just check what is the how the Z gate X. Then I have a poly Y gate. The poly Y gate 0 goes to I into 1 and 1 goes to -I into 0. And these are my circuit symbols. Then I have the Hadamard gate. What is the Hadamard gate? Actually, this Hadamard gate, we can regard it as a square root of NOT gate. And this Hadamard gate is frequently used in your quantum circuit. And what is the main main function of this Hadamard gate. Hadamard gate main function is to produce a superposition state. Now you see from the Dirac notation, you can check the Bryant gate notation, how a zero vector goes. Zero vector goes to 1 by root 2 of 0 plus 1 by root 2 of 1. So this produces superposition state. And generally, the qubit are associated with superposition. So naturally, the Hadamard and 1 goes to 1 by root 2, 0 minus 1. And this, when Hadamard gate acts on 1 by root 2, 0 plus 1, it becomes 0. And 0 minus 1 by root 2, it acts, it becomes 1 gate. So I can regard this as a square root of NOT gate, which has no counterpart in your classical gates. Okay, and Hadamard gate is something which is frequently used, and why it is used? To produce a superposition state. Now, so no, it is wrong thing. State it will become again 0. 0 goes to Hadamard gate, and it will, and ultimately it will be 1. So it is something like you apply Hadamard gate 2 times, then it is a NOT gate. If you apply Hadamard gate 2 times, then it is a NOT gate. So one Hadamard gate can be regarded as a square root of NOT gate. A square root of NOT gate. Because h square becomes equal to x gate. So all these are 1 qubit gate, but we can have also more than 1 qubit gate, and the functioning of your multiple qubit gate, 2 qubit gate or 3 qubit gate can be explained with the help of your tensor product. Already you have learned what is a tensor product. Then what is a 2 qubit gate? You see how a 2 qubit what is a 2 qubit gate can be represented, or 2 qubit state. I have a single qubit gate. What is the representation? Alpha plus alpha 0 plus beta 1. But I have for a 2 qubit gate, I have something like this one. I shall tell you the exact formula. You see here, psi 1 tensor product psi 2 is equal to A1 A2 0 0, A1 B2 0 1, B1 A2 1 0, and B1 B2 1 1. So I have ultimately the 2 qubit state. 2 qubit can be represented by a mathematical formula something like this one, which is obtained through your tensor product of 2 1 qubit. And I have again sum is therefore A1 A2 square plus A1 B2 square, B1 A2 square, B1 B2 mod square is equal to 1. Does this math support this? Yes, math supports this one, because mod of all this square is equal to 1. So it mixes with your probability concept. Then when you use general coordinates like your computational basis, the 0 0 1 0 1 1 0, which looks like this one, 1 0 1 1. So it is A 0 0 0 0 plus A 0 1 0 1, A 1 0 1 0, A 1 1 1 1. So this is actually 2 qubit state. This is a 2 qubit state. Again, I am repeating, a 2 qubit state can be represented by this one. So with this, all this formula already we have discussed. Now this 2 qubit gate has two interesting things. The 2 qubit gate state, one can be a separable state or can be entangled state. So what do you mean by this separable and entangled states? Suppose I have a 2 qubit gate, something like this one, not 2 qubit gate, 2 qubit state is something 1 by root 2 0 0, root 3 by 2 root 2 0 1 plus 1 by 2 root 2 1 0 minus root 3 by 2 root 2 1 1. Now you see this can be written as product of two states, the qubit 1 and qubit 2, 1 by root 2 0, 1 by root 2 1 into half 0 minus root 3 by 2 1. So this 2 qubit state, this 2 qubit state can be written as a product of two individual states. So this is called a separable state. But now closely observe the other one. 1 by root 2 0 0 plus 1 by root 2 1 1. You cannot write this one as a product of two states as before. That means any multiple qubit state which cannot be written as a product of individual qubit state is called an entangled state and which are not separable. This entangled state plays a very important role in quantum communication, like your quantum teleportation. Also, it is used in very dense coding, something like this one. What is the quantum communication? I want to give my information from here to somewhere. This is your communication. So how do you, we have a classical communication, we have a classical channel, you know, through a mobile, all these things, you are moving information from the one point to another point. So that is your classical communication. But this, and I use my to secure my messages or my communication, I do some cryptography and I pass my this one. But somebody may take my, he can decode this one and take my information. So I use cryptography. But to equal a secure communication, this quantum communication plays a very important role, and that too in the entangled state. So that one we shall not discuss here. So I have, there are the four states, two qubit states are very important. This phi plus, phi minus, psi plus, psi minus, all these are well states and all these are entangled states. They cannot be written in separable state, which we generally use in quantum state. Then how to know the state is entangled? That is, I can write down some mathematical formula for at least two qubit state. You see, a two qubit state can be represented as alpha gamma 0 0, alpha lambda 0 1, beta gamma 1 0, and beta lambda 1 1. And if I get alpha, this is not equal to, if we multiply the coefficient of 0 0 1 1, alpha beta gamma lambda, and 0 1 1 0 also, if I get alpha beta gamma lambda, both are equal. Coefficient of 0 0 and 1 1 I shall multiply. Coefficient of 0 1 and 1 0 I shall multiply. And if both are equal, then they are separable, otherwise it is entangled. So let we have this type of thing. Now you see CNOT gate, you must have heard about control NOT gate or not. The control NOT gate for this quantum communication, it acts something like this one. 0 0 goes to 0 0, 1 0 goes to 1 1, 0 1 goes to 0 1, and 1 1 goes to 1 0. And that too by matrix representation is given by this one. Circuit symbol is like this one. You know what is a NOT gate? What is a control NOT gate? Okay, tell me. You know or not? CNOT gate. Classical computation also have CNOT gate? No. I thought it is in. So what is control NOT gate? You know what is a NOT gate. Now you see the actually this is a classical analog is your JOR gate. Sorry. The quantum in quantum computation I have CNOT gate. Its classical analog in the classical computation we have a JOR gate. So it acts exactly like your JOR. And then I have a 2 qubit edge gate. Okay, so edge gate you have studied in detail. So I can describe a 2 qubit gate. So I am, for the time being, I am going very fast. So 2 qubit gate, 3 qubit edge gate, I can calculate. Then any qubit edge gate also I can calculate. Now you see how to generate an entanglement state. Now you see with the help of the Hadamard gate and CNOT gate, I can generate an entangled state. For example, in the right hand side, if you closely observe 0, what are the two inputs in this gate? 0 and 0. Achha. Now this 0 will go to H. What will be my result? What will be my result? 1 by root 2, 0 plus 1 by root 2, 1. Okay. Now the black point tells me this is a control bit goes here. If the control bit is 0, then there will be no change. Whatever in the lower, the cross mark is there, whatever you will get, it will not change. But if the dot mark is, you will get 1, then it will change. So can you do some mathematics here? I have not written in mathematics in detail, but I shall tell you, going there in the blackboard. Just you are getting input 1 by root 2, 0 plus 1 by root 2, 1. And here what you are getting? Here it is 0. So first term is 1 by root 2, 0. Okay. So 0, if it is 0, then there will be no change. So what you will get the answer for 0 and 0. So 1 by root 2, 0 and 0. Then here 1 by root 2, 0 plus there is no, then what is left? 1 by root 2, 1. So if it is 1, then whatever the input will not get. So what is the input here? 0? 0 will become 1. So here it is 1 by root 2, 1. Here it is 1. So I said 1 by root 2. So this is your one of the Bell state. This is your Bell state. And this Bell state is entangled state. I know that Bell state is a entangled state. So this with the help of the Hadamard gate and Synod gate, actually this combination is used to produce an entangled state from any input. Here I have shown from 0, 0. If you put 1, 1 or 0, 1 or 1, 0, anything you will get a entangled state on the right side. But that entangled state will be a Bell state. But that Bell state I know there are 4 type of Bell state. So through this combination I can get any Bell state. Then this is just a comparison between classical gate versus quantum gate, NOT gate, AND gate, NAND gate, OR gate, NOR gate, JOR gate. So similarly, I have poly gate, poly Y gate, Z gate, Hadamard gate, phase gate, W phase change, something like this. And you see in the left hand side, classical gates are there. They are restricted in number. But in the quantum gate, this is not restricted. There are many types of gates. Why? Because you know that quantum gate is a unitary matrix. 2 cross 2 unitary matrix for a single qubit gate. And unitary matrix, there are 4 entries. At least for 2 cross 2, there are 1, 2, 3, 4 entries. And it can be any number. Any unitary matrix can form a quantum gate. So there are many options available to us. So this is classical circuit versus quantum circuit. Circuit behavior is governed by classical physics. Your circuit behavior is behaved by quantum mechanics. Here signal states are simple vector like 0, 1, 0, 1, 0, 1, 1. But here it is a qubit. Operations are defined by Boolean algebra. Here operations are defined by linear algebra over a Hilbert space. No restriction exists on copying or measuring signal. But here there is a restriction. You cannot clone a qubit. You cannot copy a qubit. You can copy 0, 1, 1, 0, you can copy it. But a qubit cannot be cloned. That is why we have a theorem called no cloning theorem. Now you see a classical circuit looks like this one. A quantum circuit looks like this one. Where U are the quantum gates, it is represented by a figure something like this. Then I have a very important theorem, no cloning theorem. An unknown quantum state cannot be cloned by unitary transformation. So this plays a very important role in quantum communication. Suppose a information is passed to, just for example, Alice and Bob, and that through the quantum channel, if Eve will try to track the message, he will measure it, he will put some instrument. Once the instrument is put, the information itself is disturbed. So Alice and Bob both will know that somebody has interfered in their system. So that is, so for that, in that region, we have in quantum communication, we have BB84 protocol. That is very important. And then we have very two interesting things in the quantum communication. You must learn this one, very interesting one, dense coding. dense coding. What is the dense coding? You put classical input from Alice to Bob through a quantum channel, through the quantum channel, and that is implemented through the following circuit diagram. Just you see Hadamard gate, then CNOT gate, then UX gate is there as a gate like this one. And similarly, I have another important way of passing information that is called quantum teleportation. So what is in quantum teleportation, an arbitrary quantum state is transferred from Alice to Bob through a classical channel. So what is the difference between these two? Can you tell me? The dense coding, a classical inputs are passed to Alice to Bob through quantum channel, but in quantum teleportation, the quantum state is passed through Alice to Bob through a classical channel. Just exactly it is in mathematical language, it is called dual of dense coding. Dense coding mein information is classical bit. Okay, here the information is quantum bit. Okay, then it is passed, then in the dense coding, classical bit is passed through quantum channel, but here quantum state is passed through classical channel. So both are dual in character, and these are the things, all these things. So that's all. These are the advantages of quantum computation: speed, parallelism, large scale optimization, simulating quantum system, cryptography, and then these are the challenges of quantum computation. The challenges are many, very difficult to construct a quantum computer, because we work in the atomic scale. In the atomic scale, the electron is moving. Even if there is a small disturbance, it changes a lot. So there has to be a method similar to your classical error correction. I have a quantum error correction method. A lot of research is going on this quantum error correction. So I have an output observation interference, because there is a small disturbance, it will change the states a lot. Then decoherence automatically in the you see in the classical computation, what is happening? What are the maximum error can happen? Zero may convert in, suppose you put result is 0, 1, 1, 0. So 0 can go to 1 or 1 can goes to 0. But in quantum computation, what are the states? You have a block sphere representation. You have many states on the whole sphere. How many points? Infinite points. So any difference, any point can go to any other point. So here quantum, to correct the quantum correction is very difficult. That is one advantage. Another is decoherence. Decoherence में क्या? 0, 1, 1, 0 you are keeping in the memory, and it will remain as it is, even if there is no there is no any external force like electric field, magnetic field, it will not change. But in the quantum, qubit will automatically goes to different values, or it may error. So this is called decoherence. So this decoherence, error correction, all these are very difficult. So these are the challenges in quantum computation. That's all. I don't know how much mathematics I have given you, but believe you know some mathematics for quantum computation. That's all.
So thank you for your nice talk. But before ending this session, I would like to ask the participants if you are having any query, because sir has covered all the things like required for learning the technology, starting from the qubit to representation in the matrix form, the unitary operations, okay, entanglement along with the teleportation, everything sir has touched upon. So this is my request to the participants online or offline, whoever is having any doubt or any query, this is your best chance to ask or clear your doubts. So please come forward.
So you can email me, and basically you ask mathematics, okay, not physics of this.
Online participants, do you have any query? Okay. So I think everything is clear because sir has taught nicely and presented very well, very smooth manner, so that everybody has got it. Okay, in clear way. So thank you, sir, for giving a nice talk. So now from the department side, even sir is from United Rourkela, but still we want to felicitate him because of his nice presence and talk. So I request HOD sir. Hey. No, send him. Sir, please. Take photo, sir. Front side.
No, expertise for only 6 months. 6 months I have taught quantum computation to MSc final year mathematics student. With that much knowledge, I don't.
We are starting in this semester. So Dr. Dasal is taking. So in summer we are planning something, and if we get the engineering students, we are going ahead with that.
Yes. Thank you, sir. So for the participants, online, offline, whoever. So today now we end up the first session. We will have meet at 2:30 for our second session today. So there Dr. Amit Saha will be giving a talk online. So all of you who are physically present here, they can also join online. Okay. And that talk will be on the multi-qubit value. So actually you have learned single qubit value and multi-qubit value, but how actually these values or qubits are actually processed or used in computation, that will be taught by Dr. Amit Saha. So thank you for now. We'll come back at 2:30. Thank you.